What specific challenge does the logic of thought, LOT method address in the context of logical reasoning by LLMs? Can you elaborate on the significance of this challenge in existing neurosymbolic approaches?
The logic of thought, LOT method, specifically addresses the challenge of information loss that occurs during the extraction of logical expressions in existing neurosymbolic approaches. This issue is significant because it leads to incorrect intermediate reasoning processes, as demonstrated in the paper where key pieces of information were lost in the extraction process of link, preventing the symbolic solver from achieving correct conclusions. By extracting propositions and logical expressions from the input context and expanding them according to logical reasoning laws, LOT mitigates the risk of omitting critical information. This enhancement allows for a more faithful reasoning process, as it preserves the original input while appending logical information in natural language, thus avoiding complete dependence on symbolic solvers. Ultimately, LOT's approach ensures that the logical reasoning capabilities of LLMs are significantly improved, overcoming the limitations faced by neurosymbolic methods like SATLM, which are prone to information loss.
Can you break down the logic of thought, LOT prompting methodology step by step? Please explain each phase, logic extraction, logic extension, and logic translation in detail.
The logic of thought, LOT prompting methodology consists of three distinct phases: logic extraction, logic extension, and logic translation. 1. Logic extraction. In this initial phase, LLMs are employed to extract formal logic expressions from the input context. This process occurs in two stages. First, LLMs identify sentences that contain conditional reasoning relationships, creating a collection of relevant sentences. Next, LLMs extract propositional symbols and logical expressions from this collection, ensuring that propositions with similar meanings are represented by identical symbols. Logical relationships are established using connectives such as negation and implication, based on the analyzed meanings. 2. Logic extension. During this phase, the logical expressions obtained from the logic extraction phase are expanded using logical reasoning laws. A Python program implements these logical rules to deduce new expressions from the extracted ones. For example, if the expressions neg-A to neg-B and neg-B to neg-C are provided, they can be expanded to derive C to A through the application of the transitive law and contraposition law. 3. Logic translation. In the final phase, the expanded logical expressions are translated back into natural language descriptions using LLMs. This involves associating the propositional symbols with their corresponding natural language descriptions and combining these descriptions according to the logical expressions. The resulting natural language information is then appended to the original input prompt, effectively augmenting it with logical insights while preserving the original context, thus preventing information loss. Together, these phases enable LOT to enhance the logical reasoning capabilities of LLMs by integrating structured logical information into their reasoning processes.
Provide a specific example illustrating the logic of thought, LOT methods process from the input context to the final augmented prompt. Walk through each main step using this example and explain how logical expressions are formed.
To illustrate the logic of thought, LOT method, consider an input context where we have the statements: if you have keyboarding skills, then you can write your essays using a word processing program, and you do not have keyboarding skills. Quote 1. Logic extraction. In this phase, the LOT method uses LLMs to identify and extract logical relationships from the input context. Here, it recognizes the conditional relationship and extracts the propositions: A. You have keyboarding skills, and C. You can write your essays using a word processing program. The logical expression formed is neg-A to neg-C, indicating that the absence of A leads to the absence of C. 2. Logic extension. Next, the extracted logical expressions are expanded using logical reasoning laws. For instance, applying the transitive law, if we have neg-A to neg-C and another expression neg-C to neg-D, where D could represent another proposition, we can deduce a new expression neg-A to neg-D. 3. Logic translation. Finally, the expanded logical expressions are translated back into natural language. The expression neg-A to neg-C is translated to: if you do not have keyboarding skills, then you cannot write your essays using a word processing program. This natural language description is then appended to the original input prompt, forming a comprehensive augmented prompt that retains the original context while incorporating the logical deductions. Through these steps, LOT effectively preserves the original input while enhancing it with logical information, thereby improving the reasoning capabilities of LLMs.
What empirical results demonstrate the effectiveness of the LOT method? Please cite specific datasets and performance improvements over existing prompting methods that you highlighted in your paper.
The empirical results demonstrating the effectiveness of the logic of thought LOT method are evident across several datasets. For instance, LOT significantly enhances the performance of the chain of thought COT method on the Reclor dataset, achieving an accuracy improvement of +35%. Additionally, it boosts the self-consistency SC method's performance on the same dataset by +52%. On the Logica dataset, LOT improves the accuracy of COT-SC by +5%, and it elevates the performance of the tree of thought TOT method on the Proofwriter dataset by +8%. Overall, LOT consistently outperforms existing prompting methods, achieving significant enhancements in 35 out of 40 comparisons across 5 datasets, showcasing its robust capability in logical reasoning tasks.
In your opinion, what are the potential limitations of the logic of thought LOT methodology, particularly concerning the types of logical reasoning tasks it can effectively handle?
The logic of thought LOT methodology has notable limitations, particularly in its support for a restricted set of connectives and logical reasoning laws, which may hinder its applicability to more complex logical reasoning tasks. The current implementation of LOT focuses on basic connectives such as negation, implication, and conjunction, which may not suffice for intricate reasoning scenarios that require a broader range of logical constructs. Additionally, the reliance on LLMs for extracting logical symbols and expressions introduces potential issues, such as the repetition of expressions and omissions of logical relationships, which can lead to inaccuracies in the reasoning process. Furthermore, the complexity of prompt design in the logic extraction and translation phases increases with the inclusion of more connectives and laws, potentially complicating the logical deduction process in the logic extension phase. These factors suggest that while LOT shows promise, its effectiveness may be limited in handling diverse and complex logical reasoning tasks.
What future directions do you envision for enhancing the logic of thought LOT approach? Are there specific improvements in the methodology or new areas of research that should be explored?
Future directions for enhancing the logic of thought LOT approach include expanding the set of connectives and logical reasoning laws utilized within the framework. This expansion would allow for more complex prompt designs in the logic extraction and logic translation phases, potentially leading to improved logical deductions in the logic extension phase. Additionally, addressing the limitations of LLMs in extracting logical symbols and expressions is crucial, as issues such as repetition, omission, and deviations can compromise the accuracy of the reasoning process. Future research could focus on developing more robust methods for logical expression extraction to mitigate these illusion issues inherent in LLMs. Overall, these improvements could significantly enhance the logical reasoning capabilities of LOT and its integration with existing prompting methods.